Welcome to Solidio Gloria Physical Chemistry. Today's topic is molecular electronic structure. So we are going to talk about today the hydrogen molecular ion. Let me get the laser pointer. Okay, and molecular electronic structure. Basically, it is a configuration of electron and self-consistent field LCAO-MO approach, linear combination atomic orbitals and molecular orbitals. So at the end of the day, you will know what this is. And also we are going to talk about molecular term symbols. Okay, so first topic is the hydrogen molecular ion. Hydrogen molecule has two protons, H2. So two hydrogen atoms making a molecule, and it loses one electron. Then what we have here is two proton, two hydrogen atomic nuclei, some molecular nuclei, and then one electron only. So when you solve the Schrödinger equation of this system, you will have one electron wave function, which is orbital. So what you aim to obtain, our goal is to obtain hydrogen molecular ion orbitals. Okay, that's it. That's what we are going to do. So the system has two hydrogen atoms nucleus, proton in this case, HA and HB. And then the distance between those two nuclei is capital R, and there is one electron distance from proton A, RA, from proton B, RB. This is the kind of mechanical layout of the system. And then basically here we also apply a Bohr-Oppenheimer approximation. There are two different, dynamically different degrees of freedom, set of degrees of freedom. We can separate them. So in terms of more simpler or elementary word, it is that heavier particles or object in the system could be considered to be fixed in space. And then we are going to talk about or deal with only the lighter element here, lighter particle, electron. So only one kinetic energy term for one electron, which is, so we drop the subscript for the electron, which is -2, -1/2 del square. This is the, we are using atomic unit here, So this is the kinetic energy of electron, and then the electron nucleus, electron proton attraction, the Coulomb potential is in the full with the constant negative 1/4 pi epsilon naught, and E times minus E, minus E times plus E, positive E, and then 1/RA, which is the Coulomb term. But here we are using atomic unit, and in atomic unit it is 1/RA. And also the Coulomb potential for this electron from the proton B, which is 1/RB. And this 1/R, capital R, is the nuclear repulsion term. So this, in this case, because we fixed the atomic nuclei here, this is a constant. So this is a constant term, and then this is the Hamiltonian. And then we have, once we have Hamiltonian, then we solve the Schrödinger equation, H psi, E psi, and here, because this R is constant for this fixed configuration or conformation, to be exact, so we treat this R as a parameter for this wave function. So the parameter of this function, and the variable independent variable here is RA and RB. RA and RB are independent variable. So this is kind of the variable for this wave function. And then for this, we are going to apply variational method, variational approach here, and then we use trial function. Trial function for the variational or variational function is here. If you look at this part, this is one hydrogen atom. If you look at this part, this is another hydrogen atom. So two hydrogen atom kind of mixture here. So kind of logical way we can think of as a trial function is just a combination of this hydrogen wave function and that hydrogen wave function. So which is 1s orbital and the ground state, of course, and then 1s orbital. So 1s orbital plus 1s orbital in the linear combination, which is C1 1sa plus C2 1sb, or you may have negative combination in a way, C1 1sa minus C2 1sb. And when you deal with this variational approach, you are going to do several kinds of integrals. So those we named Coulomb integral, resonance integral, and overlap integral. Overlap integral is overlap between the two orbitals. In this case, 1sa, 1sb integrated into space, and that is overlap integral between 1sa, 1sb orbitals, which is called here SAB. And also there is a normalization condition, which is 1sa, 1sa integrated, which is SAA, 1sa, 1sb, I'm sorry, 1sb, 1sb integrated, which is SBB. Because the orbital itself is normalized, and this is equals to 1, and this we call this overlap in a sense that it is real overlap integral, which is S. Yeah. And these two expectation values or cross expectation values, I would say, of this Hamiltonian. So given the Hamiltonian, 1sa, 1sa, or 1sb, 1sb, those are the same because there's just hydrogen 1sa, 1sb orbitals, and that is we call Coulomb integral, and that in normal sense this is when if you don't include this HB, and in that sense this is just a 1sa orbital energy. But anyhow, which we call HAA and integral Hamiltonian as 1sa, 1sb, which is HBB. And as I said, if we disregard HB, in this case, this is just one hydrogen atom. That one hydrogen, 1s electron energy is E1s, and then J, that J is Coulomb integral. That J is in this case R 1 over RB here. This is the hydrogen atom 1sa, and this is the term the left of this H Hamiltonian. So kind of expectation value of minus 1 over RB, which is the Coulomb for wave function 1s, which is the Coulomb integral. So HAA HBB equals to E1s, 1s energy, plus J, that is the Coulomb integral. And if we have kind of cross expectation value, meaning is H1sa, H1sb, we call that HAB. And also in this case, these two protons are equivalent. So HAB and HBA are identical. So I missed it here, but integral 1sb h 1sa the same, and that in either case we apply Hamiltonian operator to 1sb or 1sa, and then the first and the second term will yield you 1sa 1s energy, and then there is a cross term for like this one. Okay, and also you will have expectation, cross expectation I do call minus 1 over RB integrated, that we call the resonance integral or exchange integral. In other words, a resonance integral or exchange integral, that's the same term. And so these four, I mean, actually the Coulomb integral, resonance integral, and overlap integral and normalization condition will be used in this variational approach. So I'll repeat this in the next slides. Okay, just like here. And then, so we have variational trial function or variational function, to be short, psi equals C1, which is the linear combination coefficient, 1sa plus C2, 1sb. And then the variational energy, we talked about this in the previous lecture. Variational energy, which is H psi, E psi, kind of from the left hand side we multiply with psi star and then integrate, and then you have energy which is this one for the H, and then you the other side you have E times this kind of normalization condition. So the energy is given here, integral psi star H psi d tau over integral psi star psi d tau. If the psi is normalized, this is identically 1, but this is the variational energy. Anyhow, that is not the case. We have 1sa, 1sb normalized, but not the combination. So we have the normalization condition in the denominator. So this is the variational energy. So we put psi in these places, and then what we have here, this is the psi square. Yeah, this is it. And then we expand and then integrate. For example, this is integral C1 times C1, which is C1 square, and 1sa H 1sa d tau, of course, which is HAA. So C1 square HAA, and then let me do another one. C1 SA H C2 1sb, then which is C1 C2, and SA H SB, SA H SB, which is HAV. But you will have C2 1sb H C1 1sa, which is HBA, which is equal to HAB. So you have twice of HAB term, and also C2 1sb H C2 1sb, which is C2 square HBB. Likewise, we have the denominator 2, which is include overlap integral and normalization integral, in this case SAA and SBB, which is 1, which are identically 1. And then this is the term. Okay, this is the energy. And you remember that in variational approach that the lowest energy is above the correct true energy. So you are going to minimize this one. So in order to have minimization or minimal extreme, your derivative with respect to parameter, variational parameters, is identically 0. So your energy, what you're doing is actually dE dC1 dE dC2 equals to 0. So in order to do that, what you do here, make this E equals this, make a implicit function, and then we make a derivation. So let's first make the derivation with respect to C1, and then you leave E here, and then make a derivative with respect to C1 for this term, which is 2C1 plus 2C2S here, and then this side, and then you make a derivative round C1, and then leave this term, and the other side is this, and then you make a derivative with respect to C1, which is 2C1 HAA and 2C2 HBB, and this is 0. Okay, so this is it. Now, well, you do the same for C2, and you have this one. And then here, notice that round C1 is 0 because we are going to get the minimum, and round C2 equals 0 because we need that condition for the minimum of this energy, for this variational energy. Okay, so we remove these two terms, then this equals to this, that equals to that, and then that's the next slide. So we reached here, we come up to here, and this is the relationship of those two minimum condition. Okay, so this is the linear equation in a way that we are going to get the energy here. E is kind of our unknown, and then we are going to get it from these two linear equation. What we do here, just to refresh your idea, here is that we are solving the Schrödinger equation for the hydrogen molecular ion. And firstly, we obtain the energy, and then we obtain the wave function. That's what we say we are solving the Schrödinger equation. And if you look at this equation, linear equation, if C1 and C2 both are 0, this is okay, yeah? Well, both two equation is identically 0 when C1 and C2 are 0. But C1 equals 0, C2 equals 0 is not really a solution. That's really, we call that trivial solution. It doesn't make any good for us, because which means that there is no electron. So C1 and C2 must not be 0, and then non-zero solution is obtained when the coefficient matrix, coefficient determinant, which is HAA minus E SAA, because ESAA and SAA, SBB, by the normalization condition, those are 0. That's why we dropped it here and here. Anyhow, this is the formal form. HAA minus E SAA, when this is not normalized, when the trial functions, in this other words, basis functions are not normalized in that case, HAA minus E or HAA minus E SAA and HAB minus E SAB here, this we say here, that we say 1, SAA SBB equals 1, and SAB equals S. Okay, that's why we have here and this one, and also HAB minus SABE. Okay, and this one is HBB minus E SBB, fully written here as the kind of determinant. And the name for this determinant, there is a name, which is the secular determinant. The secular determinant. Okay. In terms of these integrals, and HAA is here, E1S plus J. J is the Coulomb integral. And HAB is E1S S plus k. K is the resonance or exchange integral. And so in this overlap integral, this circular determinant is written in this way. E1s plus j minus E. This is known because this is 1s hydrogen atomic orbital energy for the hydrogen atom. And also E1s s plus k. This is the HAB term minus ES and the others. And this is the circular equation or circular determinant. And then you expand this determinant to obtain this. This is basically this times this minus this times this, okay? This way, you remember from your linear algebra. So then this is identical. So we have this square minus, this is identical, these are identical. So this square. So what we have here is basically this equals plus minus this. And from that, what we obtain, we kind of gather. Then we use this energy term, energy, with this symbol because there is plus minus, so kind of double symbol here, double energy, not the double energy, representing two different energy. One is plus and one is minus, and then you obtain this E minus E1s. This way, basically you move this, well, firstly equate this and then without square term, square, and then move this way. So then what you have is the E minus E1s. Then you collect the other side, which is J plus minus K over 1 plus minus S. And we say this is, we let this is equal to delta E plus minus, which is the difference from the orbital 1s orbital energy with this hydrogen molecular orbital energy. Okay. So basically this is the hydrogen molecular ions orbital energy minus hydrogen molecules orbital energy, which is J plus minus K over 1 plus minus S. Now, once we obtain the energy itself, which is here, which is E plus minus equals to E1s plus J plus minus K over 1 plus minus S. Once we have the energy, for example, delta E plus, E plus is equal to E1s plus J plus K over 1 plus S, like this. And then you can obtain, you put this energy here and here, and then solve, you could solve with respect to C1 and C2. You determine C1 and C2, then you determine this linear combination. And you do the same for the E minus. Then you obtain minus combinations C1 and C2. And then, which is determined, well, this equation is solved with this energy, then you obtain this. Well, for the plus case, you have identical C and C, and for minus case, you have identical C and minus C for C1 and C2 respectively. So in this case, you have to, here, you have to normalize this C1, and that is obtained when you do the normalization, and then which is 1 over square root of 2 times 1 plus minus S. That's the normalization constant. And then you obtain, for the plus case and your minus case, is this wave function, which is, for the plus wave function, we say, which is psi b, which is bonding, minus wave function, which is, we say, psi a, anti-bonding, 1 over square root of 2, 1 plus S, 1sa plus 1sb. In this case, minus and 1sa minus 1sb. Let's look into this more detail. Before we do that, yeah, firstly we normalized, as I said. So the trial function is this one. And then, because well, this is kind of, yeah, wait, let's just, yeah, this is kind of logical argument here, because two nuclei are equivalent, so these two must be the same in quantity, in size, yeah, in the value. But that is the case here by using this variational approach. Anyhow, so firstly we normalize these two wave functions, in this case plus and minus. That is done in the case C square, because you have everywhere C1 and C1 and C and C, which is C square. And then you have this kind of 1SA plus minus 1SB times 1SA plus minus 1SB. Then you have four terms: 1SA, 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 1SB, 1SB, 1SA, 1SB, 1SB. You have four terms here. And then this first term, actually you need a square bracket here. Let me have a pen, maybe. Yes, you have a square bracket here. Oops, not really good. Square bracket. And then that is C square 1 plus minus S plus minus S plus 1, which is twice of 1 plus minus S. And then that is 1. So C square is 1 over 2, 1 plus minus S. And C is the square root of that, which is C 1 over 2, 1 plus minus S. That is the normalization constant we have seen before. And then psi plus and psi minus is given here. Psi plus is for the plus sign, psi minus is for the minus sign. Okay. And this is the overlap integral. We will look a little bit more detail over this overlap integral. And overlap integral S is 1SA, 1SB, or 1SB, 1SA. But in this case, we are using real function, and which is identical to with this. And then this could be, because we have, this is 1s orbitals of hydrogen atom, and that is the function we know, an analytical function, so we can integrate it. Not that easily, but numerically, which is easy. So that is done. This is done analytically, and then this is the result. So which is e to the negative r and 1 plus r square over 3. Okay, so this is an integration result of the integration, and that overlap integral is a function of r, capital R, which is the distance between the nuclei. Okay, nuclei. So when this function overlaps, that's kind of normalization condition. So which is 1. So then the distance is 0. R equals 0, you have 1. Okay, and then it gets apart, and then overlap is reduced, getting lower. So you have getting kind of monotonically decreasing function. So which is the overlap integral. So this is what you know about the overlap integral. And then you have the overlap integral. We looked at the overlap integral, and then let's break up the contribution to the energy of the molecular ion and compare it to hydrogen atomic orbital energy. Then we know what is the kind of force, or what is the driving kind of force, maybe, yeah. What is the cause for the binding of why we are saying that this is molecule? Okay, so H2 molecular orbitals we are going to look into more detail. Which let's firstly do binding orbital or bonding orbital, psi plus. So integral psi plus star h psi plus dr, we use this way. And then we know what this psi plus is. So what this is the psi plus combination, and H is given here as the in atomic unit. And then you look at first term and second term, which is for the hydrogen atom Hamiltonian for A, hydrogen atom A, and minus 1/2 del square minus 1 over RB, which is the Hamiltonian for HB. So anyhow, if you apply this to 1SA, you obtain 1s energy and 1SA. If you apply this to 1sB, you have 1s energy and times 1sB orbital. Okay, so use these two relationship when you expand this Hamiltonian. So you have your function, left hand side just leave there, and your Hamiltonian, but you expand it. Firstly, I mean, this is the kind of, you have Hamiltonian here like with this, and then expand this, leaving this and only this part and that part, and 1SA and 1sB, 1SA plus 1sB, the operator term is the same. So you apply this. What you leave here is that with this, what you have is 1sa energy, and then what you are left is with is minus 1 over RB and SA and 1 over R SA. So that is done. And for this one, you have 1SA minus 1 over RA plus 1 over R. This is done like this. So you are going to evaluate this integral looking up to, for example, if you do 1SA, E1S, 1SA, which is E1S because 1SA and 1SA, and then that is normalized. 1SA orbital is normalized and 1sB orbital is also normalized. But 1SA, 1sB, there is a overlap integral S. And then the other one is for the overlap integral. So what you have here is 1s orbital energy from here once, and then this times this times this, that is what? Overlap integral times energy. So overlap integral times energy. So you have once over here and here another one. So you have twice of this E1s 1 plus S. Okay, so you calculated this, and then you are going to do this term, and that you have 1 term, 2 terms, 3 terms, 4 terms. Okay, so there are 4 integrals you need to evaluate. And actually this constant term is easy because there's constant term, so you just need a overlap integral and normalization integral, which is 1. But you have to calculate this 1 over electronic degrees of freedom, RB and or RA. So when you do RB for this, this is the expectation value of minus 1 over RB for 1sa orbital. This is the expectation value, this one, 1 over RA minus for 1sB orbital. And this is the 1sB, for example, this one, 1sB, this one, 1sB electron distribution, Coulomb term, electronic electrostatic charge with respect to A, nucleus A. So that is a Coulomb term. Okay. And for this one, which is 1sa orbital, which is electron, interaction with HA nucleus. So this is Coulomb term and this is a Coulomb term. Okay, so that is done. And this is a kind of similar, but there is exchange, HA, 1SA and 1SB interaction with HA. This is 1SB and 1SA interaction with HA. So these two terms we call resonance integral or exchange integral. That's why we say exchange, SA and SB exchanged. So in terms of symbol, we use J for the Coulomb integral, K for the exchange or resonance integral. So this is more, so as I say, Coulomb integral and exchange integral is this. And as I said, this is one of R is the constant. So in this case, A's are normalized, so you have just one term. And for this one, you have a overlap integral multiplied. And then, yeah, this is a Coulomb term, SA with respect to interacting with B. This is exchange term, SB and SA, 1SA, interacting with B, or the other way. A is the same. Okay, so let this Coulomb integral J, let this exchanging integral K be K, and the energy we are talking about now bonding integral, bonding integral. So delta E plus is equal to you call that, which delta E plus minus is J plus minus K over 1 plus minus S, but in this case we are using only plus sign, so J plus K over 1 plus S, but we just break these two. So this is the bonding energy, which is lowering of the energy from hydrogen atom energy into the hydrogen molecular energy, hydrogen molecular ion energy, which is a Coulomb contribution and exchange contribution or resonance contribution. So we'll just figure out their kind of size difference or contribution. Okay, so this could be done numerically or some way. We know the value as a function of R. Remember that R is the parameter. In this case, we used Bohr radius as the distance unit. So 1 Bohr, 2 Bohr, 3 Bohrs. 1 Bohr is that just about 52 picometer. Okay? And 4 Bohr, 5 or 6 Bohr like that. And the energy is in Hartree. And then we plot 1 over J over 1 plus S is here. And K over 1 plus S here. So like that. And then delta E plus is the sum of Coulomb term and exchange term. Okay, yeah. So, well, J and K is obtained this way by integration, because we know the 1SA and 1SB orbital. We could do this, and then that is plotted here. And then, if you compare this Coulomb term and exchange term, the bonding is from majorly due to exchange term, resonance term. So, quantum mechanical binding of the two nuclei into molecule or molecular ion is contributed by majorly exchange integral. So electron exchange makes the chemical bonding. That's the conclusion in this hydrogen molecular ion. So Coulomb term is here and exchange term is here. So this is the binding energy curve. Binding energy means that E, the energy lowering of the molecular entity against or from the hydrogen atomic energy. So we just see this the solid line. So lowering is majorly contributed by exchange integral or exchange interaction. So just to have in mind. Okay, so but there is another wave function, that's a bonding orbital. Well, still we are doing H2 plus, which has only one electron. So what we have here as the solution for the Schrödinger equation, which is the wave function, but that is one electron wave function, and we call it molecular orbital. Well, H2 is a molecule, H2 plus is still molecule, so molecular orbital. So the bonding orbital, we just did we have just considered the bonding orbital, and then there is an anti-bonding orbital with negative sign. So 1 over square root to 2 1 minus s, 1s a minus 1s b, so which is psi minus, and E minus the energy is E1s plus J minus K over 1 minus S. So this is antibonding orbital. And then antibonding orbital contribution with K, J, K, and S the same, and at J, K, and S the same as here, yeah, as a function of R, of course, and it's driven, I mean, plotted this one. So there is no stabilization like psi plus. Psi plus has a minimum here, and that is kind of bonding distance. So RE, in this case, it is a little bit 2 point some Bohr radius. In terms of picometer, which is 132, and there is a bonding. So H and H, HA and HB, HA and HB, the distance between them is 132 picometer, minimized in this variational approach we obtained. And then energy itself is 170 kilojoule per mole, which is lower from E1s, from the low, the 1s energy. So 1s energy. Okay, so 170 kilojoule per mole. Okay, 170 kilojoule per mole. So binding energy. That we call the binding energy. And then this one, for antibonding orbital, there is no such minimization, no such minima. There is no such minimum, and there is no bonding. This because of that, we call this orbital E psi as antibonding orbital. Okay, so this is the result, the conformation, the minimum energy, distance, and the energy from variational approach. And experimental value for that is known, which is binding energy is 268 kilojoule per mole, and then the distance, minimum distance between the two nuclei is 106 picometer. So 106 picometer is a little bit over 2 Bohr. Yeah, 104 is about 2 Bohr radius. So it's about here. And then minimum is much lower than this. So basically what you expect is something like follow just like this. I'm not sure if I can draw this a little bit carefully like this. I'm sorry, yeah, that doesn't look good. Something like this. Okay, so this is the kind of experimental expectation. We expect it must behave like this because this is from the line is from the experiment. Let's do this, and then let's get back laser pointer. So what we expect from experiment is something like this behavior, but the energy is higher, much higher in this case from real energy, true energy, That's what variational principle guarantees you. So we tried, and we will still have over the true energy. And then, but we are close to the kind of geometry of the hydrogen molecular ion. Okay, now it's a kind of more elementary or general chemistry idea. So you have positive combination of 1s orbital. Yeah, look at, let's say 1s orbital looks like just like this. Okay, and 1s p orbital is just look like this. And then this is a minus combination. That's why you have negative amplitude. This is plus combination. That's why this is minus combination, and that is plus combination. That's what you have here, like this. And then this is psi, and this is psi square. Psi square, well, psi square is actually the probability, and psi is probability amplitude. And then what you have is this red curve for the antibonding. Here you have 0 probability, which means there is no electron in between A and B. There is, and this is we call the node, N-O-D-E, node. And then there is no electron density between the nuclei, and there is no bonding. That's what we say. This is antibonding orbital. And then for the bonding orbital case, you have build-up of electron density between the nuclei. So, but here the green curve says non-bonding orbital, meaning is that you just numerically add two orbitals together, no interaction. Then that is non-bonding. The non-bonding interaction is this green. So antibonding is less than green between the nuclei. In the bonding case, more than green. The blue is more than between the nuclei. So this is what we say a bonding orbital and anti-bonding orbital. Okay, there are a couple of other views, or the types of views for this bonding interaction or anti-bonding interaction. So when I say atomic orbitals overlap, and then it ends up with overlap and positive combination and negative combination. A positive combination ends up with a bonding orbital, meaning is that there is electron density build up between the nuclei, and there is no electron density between the nuclei. We call it anti-bonding orbital. And then no electron density, in this case that's a plane, that's we say nodal plane. And then antibonding is higher in energy than bonding energy, and bonding energy is lower than atomic energies. So which is bonding energy, and that is anti-bonding energy. And this is the kind of, we say, orbital diagram. So atomic energy, atomic orbital, and then lowering is the bonding orbital, raising is the anti-bonding orbital. So this is bonding orbital, anti-bonding orbital, and there is only one electron, and with that electron is in the bonding orbital. So this delta E plus is the stabilization energy or bonding energy. And if there is one more electron, that is double, the bonding energy is doubled. That is the case for H2 molecule. So you have one electron just here and the other electron there, and then you have two electrons in the bonding orbital. So that's the way we see the chemical bonding. And then we just explain or describe 1s-A, 1s-B interaction. That's for the hydrogen molecule. But what if you have 2s orbital or 3s orbital? So in general, s orbitals could combine that way. So s orbital plus way bonding, minus way anti-bonding. Yes, bonding orbital and anti-bonding orbital. I did not say anything about this symbol, which is sigma G and sigma U. We are going to do it a little bit later. So this plus combination gives you bonding orbital. Minus combination will give you anti-bonding orbital for this s orbital interaction. Okay, so this is 1s orbitals, then you have 2s bonding, anti-bonding orbitals. Okay, just look at this. And then you have also p orbitals. And in the p orbital case, so p orbital case, there are two ways. This we say, call it head-to-head, anyway. And then here, minus plus minus plus, you will see nodal plane, right? Because the plus and minus cancels each other. So there is a nodal plane. If you have a nodal plane which is higher energy than no nodal plane case. So this is higher energy, meaning is that this is anti-bonding. And if you have minus plus plus minus combination, then you have a build up in between the nuclei, and then that is bonding orbital. So in this case, we call sigma, of course, in this case. But anyhow, this way, combining this way, you have anti-bonding orbital. Combining this way, you have bonding orbital. In this case, probably you will subtract this from that. That's why you flip, because you subtract. Okay, this is more or less plus combination. The same A and B are the same. So this is plus combination. That's minus combination. But in this case, you get minus combination will get low in energy, which is the bonding orbital. Okay, and then there is another way for p orbitals. If you have two p orbitals side by side, and then you can expect plus plus overlap or plus minus overlap. If you have plus minus overlap, there is a nodal plane which is in higher energy, that is anti-bonding orbital. And if you have plus plus combination, then there is no nodal plane, that is low in energy. We call it anti-bonding, this one bonding orbital. But this is side by side overlap. There is a kind of cosine for that, which is pi orbital. So we are going to look at this more detail or definition definitely a little bit later. And to make kind of summary, s orbital combination is done like this. So either bonding, s orbital plus s orbital bonding, s orbital minus s orbital anti-bonding. If you combine s orbital with big s orbital and p orbital, then the bonding and anti-bonding cancels. Okay, then you have no bonding situation. So in this case, non-bonding orbital. So anti-bonding, bonding, non-bonding orbital. And p orbital case, you combine negatively, you will obtain like this. Then there's a p orbital and a bonding orbital. Then that is anti-bonding orbital. Side overlap will give you also bonding orbital and anti-bonding orbital. And one rough rule of thumb here is that any orbital can combine, make a linear combination. Which orbital? Atomic orbital. Any orbitals from atoms may combine and yields you molecular orbital. But the most effective combination is from orbitals with the similar energy. We just use the same energy orbitals up to now. So two atomic orbitals must have similar energy and the same symmetry. Yes, there is a concern for the symmetry too. The same symmetry orbitals interact. Yeah, symmetry is the topic in chapter 12 in our textbook. And maybe in time, we are going to talk about that. And with respect to rotation and about the internuclear axis, that's the symmetry. So symmetry adapted orbitals we are going to deal with. So now this is the kind of definition, or I would say definition. Or yeah, this is the kind of a more detailed explanation about the notation I did not talk about before. So we use the notation sigma, pi, delta like that. Are you familiar with this? SPDF, which is angular momentum. So molecular, this is also orbital, so there is angular momentum involved. So molecular angular momentum of your wave function is 0, the notation is sigma. Angular momentum of your wave function is 1, that is notation p, pi, and 2, a delta, SPD in Greek lowercase. But usually you see sigma and delta only. So for general chemistry beloved student, we told them in a way that there is a bonding axis of bonding between nucleus A, in this case atom A and atom B. Atom A, atom and atom B, and then internuclear distance. So if the orbital is kind of cylindrically symmetric about this internuclear axis, okay, then that's a sigma orbital. And then if there is a plane, nodal plane, there is a nodal plane, meaning is that there is a electron density here and down here, up and down of the internuclear axis. So nodal plane is this. So that nodal plane included axis, then that is pi. So one nodal plane that contains the internuclear axis, then we say that's pi orbital. But in reality, I mean, in the essence, that is the notation for the orbital angular momentum. So its molecular orbital angular momentum is 0, that's sigma. If 1, that's pi. If 2, that's delta. If 3, phi. Yeah, that is the kind of notation for the orbital. So basically we have dealt with sigma orbital and pi orbital. And then there is a when you deal with only homonuclear diatomic molecules, just in this case H2, the same atom or molecule, then there is inversion symmetry. I mean center of inversion, so just in the middle of two nucleus, and then nuclei. Then if there is a symmetric, then we call it that's even symmetry, and that's gerade, German. And then if there is antisymmetric relationship of this molecular orbital, in the molecular orbital, we call it ungerade. So we put G or U as a subscript for this notation. Okay, just like this. And then if this is a bonding orbital, there is nothing more. If that's anti-bonding orbital, we put superscript star. So yeah, just like that. So that is the orbital notation. We'll get back this, we'll use this all the time later on. Okay, orbital ion, hydrogen molecule ion. Now we have real molecule. Well, actually, hydrogen molecule ion is also real molecule, but no ion, but just a neutral molecule. So H2. So H2, for the case of H2, and there are 2 electrons now and 2 nuclei, but with the Bohr-Oppenheimer approximation, we just keep the nuclei fixed in position. Yeah. So HA and HB, the 2 nuclei is fixed in position in distance r, and then that r is the parametric act as a parameter, and 2 electron move here. So electron, yeah, this is full Hamiltonian for this 4 particle system. So nuclear motion and electronic motion, and electron nucleus interaction, these 4 terms, well, 1 interaction, 2 interaction, another 3 and 4 interactions just here, and then nuclear repulsion. So this is the full Hamiltonian, but with the Bohr-Oppenheimer approximation, we kind of separate A, B motion from 1 and 2 motion. So, and then treat for 1 and 2 motion, we fix the position of the heavier nucleus. Okay, so just to remove this, and then you obtain this. So electronic kinetic energy, electron repulsion energy, nucleus repulsion energy, electron nucleus interaction energy. In atomic unit, you just put in this simpler form. So we are going to solve H psi E psi. Okay, that's what it is. Schrödinger equation. Okay, so now I forgot to mention that H2 plus case, there is an analytical way to solve it. Actually, that is another term, probably Schrödinger himself did not solve it. But with using elliptical coordinate, you can solve it just as we do for hydrogen atom analytically and obtain analytical wave function for hydrogen molecular ion, that orbital. But here you have 2 electrons, just like what? Helium atom, which has 2 electrons. That's why you could not obtain analytical wave function. So you have to utilize what? Approximate method. Both you could do either perturbation theory or variational principle. In this case, this will not, well, for hydrogen molecular ion, we did not solve it analytically. We just utilized variational approach to obtain its wave function. You remember that? Yeah. Okay. But in this case, we have no other choice. So we utilize, firstly, variational approach for hydrogen atom. I'm sorry, hydrogen molecule. 2 hydrogen atoms and 2 hydrogen atomic orbitals is given here. And then we'll make a linear combination of those two, to make what? The molecular orbital trial function. For the molecular Schrödinger equation. So in this case, you have 2 electrons. Then the best way or simpler way to construct their total wave function is to use Slater determinant from the previous lecture. Because, yeah. So Slater determinant of 2 electron is 1 over square root of 2 factorial normalization psi b. Well, you remember this orbital diagram. So 1s A, 1s B, and then there is a sigma. Yeah, this is a sigma orbital. And then G means that H2 is just like, well, this is the let's put this as a nuclei position, and then sigma orbital, just sigma 1s orbital is just like this. And then there is an inversion center. You cross the term, you have still the same sign. That sign, same sign, meaning is that that's symmetric. So gerade. So sigma G 1s, and that's sigma U 1s, because you have this and this, and you change the sign. So sigma U 1s, and then maybe if you are really kind, then you may put star here to denote it as antibonding orbital. Or if you just drop U and G together, and then sigma and sigma star will tell you which is which. So that's equivalently good notation. So anyhow, so this orbital only, so that orbital is plus orbital, and plus orbital or psi b orbital. So psi b orbital is only, but one orbital is with alpha sign, alpha spin, and the other orbital is with beta sign. So there are 2 spin orbitals. So one spin orbital is occupied by electron 1, the other spin orbital is occupied by electron 2. Okay, so that is the combination. So that is the slated determinant will give you. So if you expand this, what you obtain, psi B1, psi B2, the same spatial orbital and your spin orbital combination. Okay, so your spin orbital combination is given, and then you can utilize it in your when you are evaluating the electron integrals. So your molecular orbital psi-MO is actually here, included now in terms of SA orbitals, SB orbital. And then you are now having 2 electrons, so 1 electron and 2 electrons. So molecular, you remember that H2 plus orbital, H2 hydrogen molecular ion, square root to 2, 1 plus s, and this one. Okay, now we have another electron, so this is it. Square root to times square root is just this, and then this times this. So that's molecular orbital. And then you will get the variational energy or energy by integrating this psi and another this. So this integral, but you have to integrate both R1 and R2 because you have 2 coordinate, 2 electron. So you obtain delta E plus delta E minus, that's the antibonding energy. So it goes up, but that goes down and settled here in the minimum. And what you obtain with, you've done variational approach already here. Okay, and with this trial wave function, you obtain the energy, the binding energy is 0.0990 Hartree, which is 260 kilojoule per mole. Remember that what it was for H2 plus ion, which is 170. So it's less than twice because electron repulsion. And then the distance between HA and H, which is 1.61 Bohr radius, which is 85 picometer. Okay, that's picometer. And this is shorter than H2 plus. And the experimental value is 0.164 Hartree, which is 457 kilojoule per mole, which is a lot higher, because you're still under kind of protection of the variational principle, which is your energy is always higher than true experimental, just like this. And then experimental, the geometry is 1.4 Bohr radius, 74.1 picometer. So I think that the geometry is kind of a little bit more tolerable than energy error or discrepancy from experiment. Now, that is the kind of minimal approach. You just use 1s orbitals only, and then your variational trial function is not that flexible. Only you have 2 parameters, variational parameters, meaning is that C1 and C2, the combination coefficient. And then, but in the variational approach, you have flexibility to make your trial function as flexible as possible. Then you will get the lowest energy, but that is still guaranteed above the true energy. So you try and obtain the best result as you could. Okay, so we now do extend the variational treatment for the H2 molecule. One of the way is just look at, this is like a classical argument, is that your trial function, that is kind of not so great. I was going to say terrible, but not so great. The slated determinant with the trial function we just used has 4 parts. Like 1SA, 1SA, yeah, and 1SA, 1SB, 1SB, 1SA, 1SB, 1SB. I did not switch the electron coordinate, so this is the order. But if you look at this one, this is okay. 1SA has one electron, this is okay. 1SA has one electron, 1SB has another electron, 1SB has one electron, 1SA has another electron. But in this case, 1SA has both electrons. This 1SB has both electrons. So this is kind of a H plus H minus combination, just like this. Okay? Yeah. Just like this. Just like this. Okay? So this and that term is either HA plus, HB minus. This is one. Then this is HA minus, HB plus. Okay? This one, and that's that term. And this one is kind of just H plus H term. So 50% is kind of ionic in this case. Yeah, H plus ion and H minus ion. H minus ion, H plus ion. And another 50% is atom and atom. So in this case, we call this covalent terms. We call these two ionic terms. Obviously, in this case, the first trial function treat this ionic and covalent term in the same ground, same kind of capacity, which is not the case for hydrogen molecule, which is most of the time neutral. So now we construct this as a covalent wave function, and that with these two ionic wave function and linear combination of that, and then that linear combination coefficient C1 and C2 as what? Variational parameter. And then we do the variational treatment. What we obtain is that binding energy is 386 kJ per mole was, without doing this, was 260 kJ per mole. And experiment was 457 kJ per mole. So we are getting about very close. Then it's about 200 difference, but that is about 130 difference, something like that. So we kind of reduce the energy and getting close approach to the experimental value. And then we also improved that equilibrium geometry from 85 to 74.9. Actually 74.139 picometer is the experimental value. So this riddle, this is one step, a little bit more extension of the variational approach will tremendously improve your geometry. Okay, and now, so kind of every possible opportunity is used to make flexible the most flexible molecular orbital trial function. In this case, what we call Hartree-Fock limit, and also SHF, self-consistent field Hartree-Fock method. You remember that? Yeah. Use kind of infinity many, but there is a kind of limit for that, saturation for that. Colles and Bonivitz used 100 term like this, and then obtain eventually 457 kJ per mole experimental value and 74.140. Very close. Yeah, this is picometer. So as I said previously, experimental value and more accurate than experimental value, or more close to truer value, could be obtained by approximation method. Approximation meaning is that we don't have analytical solution, but numerically we can getting closer, closest possible to experimental value. So now I will just to explain a little bit detail or make a summary of self-consistent field LCAO LCAO-MO approach. LCAO means linear combination of atomic orbitals. Now, we would say we obtain all atomic orbitals of all atoms, and then we can combine those atomic orbitals to make molecular orbital. This is kind of rather reasonable because eventually atoms bind together, make one molecule. So we use atomic orbitals to make molecular orbitals. That's the logical way to do. And then we achieve the self-consistency among these electronic interaction. So we kind of make a trial function as flexible as possible with given atomic orbitals, and that is a molecular orbital trial function. And then you apply Hartree-Fock-Rotan method, which is kind of mathematical way of solving the Schrödinger equation, matrix way of solving Schrödinger equation, and then determine this C1, C2, C3, this coefficient. And then all these atomic orbitals already given. What you have here is your molecular orbital. Okay, but instead of using real, say, atomic orbitals, we could use, because atomic orbitals here are used as basis functions to expand molecular orbital. And then that basis could be other functions, just like Taylor series, something like that, which is terrible, really terrible here. And then Slater proposed to use Slater, some kind of atomic orbital like this, but we call it Slater type orbital. Slater orbital, in short. Slater type atomic orbitals, just like atomic orbitals, the spherical harmonic times the exponential, just the same exponential or similar, but with the zeta different, and then only single term for R, because this was this is Laguerre polynomial. It's Laguerre polynomial. It's a polynomial, but Slater just to use just a single term, or break up the Laguerre polynomial into single term, and that he calls utilize this type of atomic orbital. So we call that Slater type orbital, STO. 1s STO is just same as just normal atomic orbital, because in the case just one term which is kind of constant. And then that's Slater type orbital. But Slater type orbital is a little bit difficult in terms of computation. It takes longer time than anything else. So anything else is a Gaussian type orbital. It looks similar, a little bit less accurate, but you can use as many as, because Gaussian orbital, Gaussian function times Gaussian function is still Gaussian function at the different center. So Gaussian orbital calculation is faster. That's I would just add. A Gaussian orbital is instead e to the negative psi r, that is e to the negative alpha, maybe the same kind of similar coefficient, and r square. This is Gaussian, that is Slater type orbital, exponential. This is exponential, but that is Gaussian. And then there's a normalization constant. So we use many Gaussian functions and expand molecular orbital on the basis of Gaussian orbitals. Okay, that's the approach in self-consistent field molecular orbital calculation, SCF-MO calculation, or more, that MO is coming from linear combination of atomic orbital, combining atomic orbitals in Slater type or in Gaussian function, and we do the molecular quantum chemistry. And I plan to give you a lecture utilizing molecular orbital calculation, or just how to do molecular orbital, kind of cookbook for the molecular orbital calculation and how to utilize the result. Maybe next lecture. Okay, so this is the result for Hartree-Fock limit for hydrogen molecule H2. So you have a simple combination, and then you just use the naive 1s atomic orbital nuclear charge, and then your energy is 1.90990, and then binding energy, you just subtract the -1, subtract this, which is this. -1 is your orbital energy. Because you see, 1s orbital energy is what? -1/2 Hartree. So you have two of them. So -1 Hartree. So minus, that's how it works here. Just this right hand side of your decimal point is your binding energy. So bond length is this. Then effective charge, you have a variational parameter. Then the still same molecular atomic orbital, but with the effective charge zeta in the exponent. Use it variational parameter and minimize it, and you obtain this. So improve your binding energy is improved. Experimental value is 0.1642. So you improved, increase approach here, and then your bond length is decreased. That's the problem. The problem here is that your energy is guaranteed above the true value, but your geometry is not. But the good news is that geometry is getting faster into the experimental value. So 38 is less than, but close, getting closer. Experimental value would say 1.41, yeah, something like that. Just keep it like this. And then this is the equation. I mean, the flexible, kind of most flexible variational trial function. And then there are many ways. So fixed nuclear charge case, then this is the result. Geometry is good already. And this is the result. And then there are 1, 2, 3 variational parameter, more variational parameter of the nuclear charge. Then you obtain a little bit better result. But Hartree-Fock limit, as flexible as possible to the limit, you get this. So your energy is far above the experimental value. So your binding energy is not that much recovered, but you have the geometry correct. So you have to go beyond Hartree-Fock approximation, Hartree-Fock treatment, which is you include configuration interaction, CI calculation is necessary. So you will get to know about this later on as you go further into the quantum chemistry era. Okay, so last topic, we are going to talk about a little bit about molecular time symbol. You see, you remember when we talk about the atomic time symbol, because you have more electron than more than two electrons. So you basically have electron 1 wave function product with second electron wave function. So you want to have single symbol to designate the state of this orbital product. So here the same situation. You have more than 2 electrons, so you are with orbital product, and you want to have a symbol to denote the state of this orbital product or the state of the molecule. Again, we utilize total angular momentum, which is the sum of spin angular momentum plus orbital angular momentum. But here we use only orbital angular momentum quantum number. So orbital angular momentum quantum number is kind of combined together. It's a vector model. It's not really scalar sum. It's a vector model. So vector sum of orbital angular momentum will give you total angular momentum here. And then absolute value of the total angular momentum 0, 1, 2, 3, 4, 5, which is SPDF, of course, here in capital Greek, sigma, pi, delta, phi, gamma. This we call eta. I'm sorry, not h. So anyhow, sigma, pi, delta, phi, gamma, like this. And then that is here in this lambda sign. And then in the superscript, left-hand side superscript, we put 2s plus 1. That s is the total spin multiplicity. This is spin multiplicity, 2s plus 1 at the left-hand side superscript here. And then there are two more signs comes here. One is plus minus and or G or U. G or U stands for gerade, ungerade, meaning is that this is only you have homonuclear diatomic molecule like H2, N2, O2, like that. That's because there is a symmetry inversion center. So if you cross that inversion center of symmetry, if you wave function product, total orbital product, switch the sign, then that's ungerade, antisymmetry. If that has still the same sign, that's gerade. And then you put G or U accordingly. And then plus minus sign is that if there is a vertical middle plane, we'll look at what this is in the next slide. And then again, with respect to this plane, if there is no change in sign, that's symmetry, that's plus sign. If changes sign, that's negative sign. This applies only for total angular momentum zero case, which is sigma state only. Okay, sigma state only. That's recall that's sigma state only. No other state, pi, delta, phi, etc., does not have plus minus notation. Okay, there are also two rules. You remember the Hund rule like that? And all field shell we disregard technically. All field shells are 1 sigma plus G, totally symmetric. So only we treat outer shells. Okay, that's what it said. All field shells, meaning is sigma 2, pi 4, delta 4, like that. Those functions, those state we call those closed shell or field shell. Those are totally symmetric. And then this is the notation for totally symmetric state. And then that's kind of the that combination yields you just everything cancels out. So you need to only deal with only outer shell, meaning is that outer electron. In the case for the case of atoms, it's you could just call valence shell only. Another thing you need to know or have in mind is the state of the hole is state of the electron. Meaning is that if you have pi 1 or pi 3, if you are dealing with pi 3, then what you do is just to do pi 1 instead. Okay, so just to simplify your work. Okay, so let's do one example. B2. This is the electron configuration of B2. B2 is boron itself. Boron atom has atomic number 5, so you have 10 electrons. So this is the orbitals, molecular orbitals you obtain from the linear combination, and then sigma G, sigma U from 1s orbitals, sigma G, sigma U from 2s orbitals, and 2p orbitals now do side overlap that is low in energy. And then 2, 4, 6, 8 electrons, and then you have 2 more electrons and 1 each electrons here. Okay, so these 4 shells are all filled, and then you don't have to consider those are totally symmetric, and you only consider this. So this is reduced to this. Okay, so that's boron 2, B2 electron configuration, molecular electron configuration, of course. Then there are ways to combine, ways for these 2 electrons. Either have plus alpha alpha, plus and plus minus as spins concerned, or minus spins. Okay, plus minus spins, and then their spin momentum is either is a sum, just a simple sum, 1, 0, -1. Okay, And then orbital case, it can contribute 1 or minus 1. So 1 plus 1 is 2, 1 plus minus 1, 0, minus 1, plus minus 1, minus 2. But in this case, both are plus or plus 1 plus 1, but which means that those are identically the same. So this cannot be there. For these 4 terms, against Pauli exclusion, no 2 electrons can have the same set of quantum numbers. So those 4 are removed, and then you are left with others. These 1, 2, 3, 6, 1, 2, yeah, 6 configurations. So let's get them into know what those are. Basically, what you have is the 0 ml equals 0 or 2. 2 cases p. I'm sorry, that's sigma, pi, and 0 case is sigma. So sigma or pi. So pi case here, and you that's it. Okay. So in the case of ml, absolute value equal 2. So which is pi. I don't have it here. Any pi. I'm sorry. 0, 1, 2. 0, 1, 2. That's why I was kind of a little bit confused. 0, 1, 2. Meaning is that sigma pi delta. I'm sorry. So ml equal to, that's delta. But this delta is plus and minus. So s equals 0. So s equals 0, meaning is that 2s plus 1, 2 times 0 plus 1 is 1. So delta 1 and delta 1, and then delta 1, that's delta 1. And then this is homonuclear diatomic, and then delta 1, if you cross the center of symmetry, that does not change that does change the sign, just like this. This pi bonding orbital, you see, this is orbital notation. This is molecular notation. That's why, even though that's pi orbital product will give you delta state. That's how you say it. So this pi orbital looks like this. So pi 1 orbital and another pi orbital, they kind of perpendicular each other. So there is central symmetry in between. The one nucleus here, the other one nucleus here. There is central symmetry. If you cross the center of symmetry, you change the sign. So each pi orbital is u orbitals, Ungerade orbitals. But you have 2 pi orbitals, Ungerade times Ungerade. So Ungerade times Ungerade is cisgerade. Minus times minus plus. Okay, that's the rule. So Ungerade times Ungerade will get Gerade. So all orbitals are Gerade orbitals because each Ungerade orbital has one electron, and then Ungerade orbital times Ungerade orbital will give you Gerade molecular state. So all have G sign. And then this is delta, no sigma orbital. So that's it. That's the sign for this ml equal 2 case. And also, now ml equals either, yeah, all zeros. But ms case, you could have -1 plus 0 and plus 1, which is what? S equal 1 case. And only this, just one case here, plus and minus, which is 0. Then that is S equal 0 case. So S equal 1 case, you have multiplicity, S equal 1 in this case. 2 times 1 plus 1 is 3. So this one is sigma, because ml equals 0, and multiplicity is 3, and then that's Gerade, and then let's look at plus or minus sign. So plus or minus sign is that your nodal plane here is, if you have nodal plane just like that, and you cross once, and you have what? Change the sign, antisymmetric. This is symmetric, so symmetric times antisymmetric is antisymmetric. Okay, so you have two cases like that. So you have minus sign. One is symmetric and the other one is antisymmetric. So that is totally antisymmetric. So this is it. And then for this case, you have multiplicity 1. So sigma 1 sigma minus g minus. So this is other state. And also this is the highest multiplicity, and that is the ground state according to the Hund law. Okay, this was a little bit lengthy lecture. So thank you for your patience, and then I hope you know most important things in molecular electronic configuration. Thank you.